welcome. It's great to be here. This is an exciting schedule. As you know, it's the 10th MagLab Theory Winter School. The topic is non-equilibrium quantum matter. I was really impressed with what the organizers put together. And I came up with a couple of main questions. A petition couldn't help me come to that we want to address during this conference, which was, can we simulate non-equilibrium dynamics on intermediate scale quantum computers? And the second one is, can we manipulate quantum states while fighting decoherence? Both aspects require a deep understanding of the dynamics of quantum matter far from equilibrium. But I'm going to leave that to you because that's your specialty. What I'd like to do now is take over a little bit because we can't do the normal review of the MagLab and have a tour, etc. We can't even go to Wakulla Springs. So I'd like to give you a bit of a overview of the MagLab. And so I'll start with this, but what I'm going to do, just to let you know, is I'm going to focus on areas that you're not that familiar with, except two slides, which you will be covering in this winter school. So first, I'd like to give my general introduction, which is the National High Magnetic Field Lab is in 3 different campuses. The main campus is right here in Tallahassee. Here's an overview of the building. I wish you could be here and see how mammoth it is. When I walk from my office to my laboratory, my Apple Watch gets very happy with the step. It's an amazing, it's a huge and just fun to see, and I wish you could come see it. We're well known for inventing new kinds of bitter magnets, the Florida bitter, that made it possible to come to 45 Tesla in a hybrid DC magnet field system. So by hybrid means it's a combination of superconducting and resistive magnet. We also have 900 megahertz, 105 millimeter Bohr, 21 Tesla NMR MRI magnets. We have a few 21 Tesla magnets. I'll give you some examples as we go along. In Florida, in University of Florida, down the road in Gainesville, we have 2 user facilities. I'm not going to label all the user facilities because you guys aren't users, but come back to me if you're interested. One that I will show some examples from is the Advanced Magnetic Resonance Imaging and Spectroscopy facility. This does MRI up to 21.1 Tesla. I'll give some examples from that. And the high B over T facility. B is not that high, but T is very low. So this can go 17 Tesla at 0.5 millikelvin for weeks at a time. Finally, at Los Alamos National Laboratory, we have the highest field pulse magnet that's non-destructive. It can go as high as 101 Tesla in a pulse, and it's got a 10 millimeter Bohr. Okay. If you're not talking, could you mute? Because I'm still let that stuff bother me. Okay, so just to give you a background of some of our magnets, and this is year versus magnet strength, and I will just show at this snapshot here that the MagLab has the records. These are the ones circled. I mentioned the 101 pulse non-destructive, the 45 TDC, but there are some other magnets that are very, very important. For instance, a 32 Tesla user facility that's all superconducting, which keeps things very quiet because you don't have all the water rushing through because there is not a resistive component. And we also have a 41.4 resistive magnet. And there's something which we call a series connected hybrid, which is also extremely stable. And at 36 Tesla, it's homogeneous enough to actually do imaging. So these are our latest and greatest hits. I mentioned the 36T series connected hybrid, that's from 2017, and the 2017 resistive magnet, the all superconducting magnet. In 2018, I'm just going to mention this one and go on, we were able to make 41.5 Tesla. It's an all superconducting PEP coil, a high TC and a low TC superconductor. And this helped in the proof, the 32 Tesla all superconducting in this, we're in the proof that we can actually build a 40 Tesla all superconducting user facility. And we were just funded for the design support for that particular user facility, which we're all very excited about. So to remind you, the MagLab attracts people from all over the world. We have over 2,000 users from over 150 institutions across the United States. And there we can see where people are going to Los Alamos, Gainesville and Tallahassee, but also from all over the world. And in fact, there are people from other MagLab user facilities around the world that come to Tallahassee, Gainesville, and Los Alamos to do their work, because not only are our magnets very high, but we're specifically known for developing our techniques and our probes and our tremendous faculty that really helps users. And in going in that direction, I want to mention that users are welcome. Every year, about a quarter to a third of principal investigators have never been to the Magnet Lab before. So our faculty are just outstanding. You just go online and you want to do an experiment, you can contact a faculty member, ask for help in writing a proposal, which is not a big deal. It gets reviewed, and you can, and then user facilities are free to use. You just have to get here and need a hotel, or I have a big house. Now, I also want to point out that this always comes out, what is the bang for the buck? The user program has had so many refereed papers in high-profile journals, and you could argue this is so much more massive and helpful to the scientific community and to our nation than splitting up into separate user facilities, because these kinds of what we can do, no one else can do in the world. And I want to give some examples of what we can do. I will try not to go over, but I will go 3 or 4 minutes over. The main themes are materials, energy, and life. And I will give some examples from each of these, because I think this group would like to see the scientific examples. Know this one already. Nick Butch will be speaking on Wednesday at noon, and this is from his group. It basically started a whole new field without going into a lot of detail. At certain angles in this uranium tellurium compound, heavy fermion, you increase the field. The superconductivity is killed, as you expect at high field, but then there's a re-entry phase at very, very high fields. This is a combination of 2 user facilities, both the DC facility in Tallahassee that goes up to 45 Tesla, and also the pulse facility in Los Alamos. So this is several facilities working together. This is very exciting. Nick will give you a lot more examples. I wanted to stress something that isn't as well known in our field, which is ion cyclotron resonance. This uses about a 21 Tesla high homogeneity wide bore magnet. This gives you a mass resolution in complex fluids of just over 1 electron mass. And so what you do is you spit in, let's say it was developed for oil, because oil is the most complex fluid on the planet, and you can get a mass spectrum that is amazingly high resolution, more than anything else on the field. Even this is how quantum time of flight looks, which is another mass spectrometer, and this is what we get from ion cyclotron resonance, or ICR. We use it for petroleomics. That's what it was developed for. We can do forensics for an oil spill. If BP and Exxon strike the same well in the Gulf, did they hit the same reserve or not? Not the same well, I should have said same reserve. It costs about $1 billion to drill a well like that. They want to know if it's safe or not.
然后有的时候我又不想让它把我叫起来，因为那张图我实在是说不出东西来，我就想。
I wish I could understand that. I need a little more. Anyhow, we also do petroleomics. There's an example of P53. As many of you know, that the folding determines functionality. So there's one famous protein called P53. Its folding can tell you if it's malignant or non-malignant. And through a deuterium hydrogen exchange, looking at these masses, we can tell the difference. I'm going to give you some examples now, I think 2 of them, that relate to climate change. The second most complex fluid on the planet is dissolved organic carbon. And so we can identify insoluble versus soluble carbon compounds and classify carbon in the Arctic permafrost. We're the only one on the planet that can do that. So here's some examples here. We go around collecting samples. Here's the Arctic Great River Observatory. And what you can do by collecting these samples and looking at the dissolved organic matter is you get insights that gives you the carbon isotopes that are there and how these things change with time. As we look at the built planet, we can tell, no one else can tell this. If you look at these complex carbon molecules, they can have different forms, an island configuration or an archipelago configuration. Some of these dissolve and some don't. Some are good for the planet and some aren't. You need this kind of resolution to actually determine the differences. Now, since this isn't, since you guys are mostly condensed matter physics, I'm going to have a couple more examples that have to do with life. And this is something that, that MRI goes high definition. When you go into an MRI in a hospital, what they're looking at is the water. They're looking where the blood accumulates. It's doing MRI imaging the hydrogen. As many of you know, when MRI is performed, there's a resonance condition between the applied magnetic field and the applied RF frequency. So the higher the magnetic field, the higher the frequency. Conventional MRI, when you go into the hospital, is about 2 to 4 Tesla. The resonance condition gives you about a millimeter resolution. If you go to 21 Tesla, you can go now to microns resolution. So now you can see subcellular structures. An example I like to bring up is the detection that the MagLab has been working. We have 3 different directions of looking at amyloids, early onsets of Alzheimer's, and Parkinson's. This is mostly in Amherst in University of Florida, but several of our user facilities work together on this. So it's believed that amyloids are directly responsible for Alzheimer's. As amyloids grow, they cause very small lesions in the brain. These lesions, called microhemorrhages, that appear as hyperintense areas. Remember, MRI picks up those protons. The higher the field, the higher the resolution. So if someone has properties that they have taste, memory, whatever, they can go get checked with this and see if there are microhemorrhages that may be the onset of early Alzheimer's. So here's an example of 50 micron resolution of these hyperintense areas in a rat brain. And here's one that's been around for a while, which is we have looked at almost the entire periodic table. So here's an example of, it's been around for a while, of looking at sodium. Instead of imaging the protons, let's look at a much heavier element, sodium. The resolution will be lower because the frequency that you need to image at that heavier atom is lower, but you are specifically imaging the sodium. This is just one of many, many, many examples. Let's look at sodium in a mouse brain. Why? It turns out when cells start to die, they uptake sodium. The details are not completely understood, but they do. So here's an example. Before I got to the MagLab, I didn't know that you could actually buy a rat with brain cancer, but here's an example of a rat, and there's imaging on the left side of the sodium. The rats are fine with this, doesn't hurt them at all. But there's the tumor. You give the rat chemotherapy, wait 4 days, see if anything happens, try another regime of chemotherapy, try again. If the tumor lights up, that means there is more sodium, it's uptaking sodium, and there's an example that the cells are probably dying, and that gives you some confidence that this regime of chemotherapy may be useful. So I just thought I'd give one more that's related to this workshop. Steve Hill will talk about this. It's my last slide, except for the schedule, and because Steve is the last speaker, and he will fix up everything that I say wrong. But we have the first observation of dynamical generation of spin polarized current. There's an antiferromagnetic material that you have terahertz radiation input, and there's subsequent conversion into electrical signals. This is spin pumping. This is toward, so this is what happens is terahertz spin goes into the adjacent metal, which is converted into a charged current, and then a charged voltage through the so-called spin Hall effect. I had to put that in. This is towards control generation of coherent terahertz currents, which is presently 2 to 3 orders of magnitude higher than current spintronic devices. I just wanted to stress this. I know Steve will talk about it. There's 4 institutions in the US, one from Norway and one from China, that got together to make this discovery. I'm going to end to thank our organizers, Hitish, Vidika, Roderick, and Kun. This is an amazing schedule. I want to thank our speakers, and I want to thank our attendees. looks like a wonderful conference, and welcome to the MagLab.